This is a mic check in case anybody's out there watching. Feel free to indicate that you hear me in the chat if so. Hey everybody, hope you can hear me. Coming to you live from the new Goldendale Observatory. I'm Troy Carpenter, and this is episode number 8 in our Goldendale Observations series. I'm hoping to keep the show short tonight because I don't want you inside watching me. I would like it much more if you were outside watching the natural event unfolding. The one that we're going to be talking about tonight, the Great Conjunction. It's not something that happens very often. You may have heard some really huge numbers associated with that statistic, that it's a rare event. You might be disappointed to learn that it's a little more common than you think, but it's still rare enough that it's worth your time to go outside and actually, watch it. The good news is you don't have to wait until the last second. You don't have to wait to the moment of greatest conjunction. You can watch this unfolding right now, or last week, or next week. The event itself is not until the 21st, but again, you could have been watching it all year. In fact, I have been watching this conjunction unfold all year, and it's kind of exciting to watch as these two famous bodies get ever closer. And those two famous bodies are, of course, the planets Jupiter and Saturn, the two best planets, at least that's my opinion. The reason that a lot of people call those two the best planets is because they are very interesting to look at through a telescope. Jupiter and Saturn have amazing features and details that can be resolved even with relatively low quality hardware. You can see the clouds of Jupiter, for example. You can see the rings of Saturn, and you can see the moons orbiting both planets. We're going to talk quite a bit about that tonight. Now, like I said, I'm going to try to keep it short, but I've been wrong every time I've said that so far, so it wouldn't surprise me if this goes 10 hours, and of course I'm joking, it better not go that long. But it wouldn't surprise me if it goes a full hour, although I am going to try to keep that down a bit. On that subject, please ask questions, even if they lengthen the show a bit. I think it's worthwhile. One of the cool things about Goldendale Observatory is that we are a public facility, we are a public observatory, and we encourage education. We exist for that reason. So ask questions, make comments, and that will enable us to tailor the content to your liking and your educational needs. All right. Now, let's get right down to it. I would ask a question, but I already know the answer. If I said, how many of you have heard about the Great Conjunction? I'm pretty sure 100% of you have. And the reason that I'm sure of that is because it's been all over the internet. And of course, as per usual, it's being hyped up to an extent that might create some, let's say, optimistic impressions of what you're going to experience. And so we're going to hope to temper those impressions a little bit, those expectations a bit. Hopefully you won't be too disappointed by the Great Conjunction. Very similar to the hype surrounding the Great Conjunction. This week, there was a lot of hype surrounding a possible geomagnetic storm that would make it possible for people to see the northern lights in places they normally can't. Like, for example, the entire continental United States, which is a little bit ridiculous. I didn't expect it, although I was monitoring the KP index, which deals with the instability of Earth's magnetic field. It did become unsettled at the time they expected, but we didn't have the geomagnetic storm that would have made it possible, like I said, to see the aurora in places you wouldn't normally see them. If you lived in Canada, yeah, you got to see the aurora, but if you lived in most of the United States, no, you didn't. Okay, so I just saw a question. What direction should we look in the night sky? The good news is that one of the objects involved in this event is among the brightest in the sky, and that's mighty Jupiter. So if you look to the south, specifically the southwest, you will see a very bright object. That is the mighty king of planets, Jupiter. And to his upper left, you'll see a dimmer, slightly more, let's say, tan or orange color object. That is Saturn. I encourage you to watch them night after night after night. And what you will observe is them getting ever closer. So let's start with a science question on that subject. Are they actually getting closer? Are Jupiter and Saturn careening towards some kind of cataclysmic collision? Are we about to see these two mighty planets destroyed by their own impact? Is that what's going to happen? Is that what we're about to see? What do you think about that? Is that a ridiculous statement? I'm going to watch the chat. Are you expecting a calamity? Are you expecting the worlds to collide? Oh, very good. Thank you. That very important word, perspective. This is true of many things in space science, and if you've watched any of the other episodes we put on from this observatory, we often talk about that word perspective because we live on a planet which moves, surrounded by other planets which move, all of us orbiting the same star, Our line of sights are always shifting. Our perspective is always changing. Many events are figments of perspective. For example, eclipses. You could argue it's something going in front of something else, but that's only if you're in the right place to experience that coverage of objects. Occultations, where a big object covers a little object. Again, you have to be in the right place to see such a thing. If you see a transit, where a small object goes in front of a big object. Again, this is a figment of perspective. Back in the year 2012, we had a very exciting Venus transit. Hold this thought, 1 second. All right, so watch this. We're going to go to our Venus transit. All right, so I shot this back in 2012 from New Jersey. And as you can see, that ball on the upper left is the planet Venus crossing the disk of the sun. Now, I was on the East Coast, of course, New Jersey, that's where that is. And as a result, I was not able to see the entire transit because the sun set. If you had been on the West Coast, you could have seen the whole thing. But in both cases, either East or West Coast, you're still on the planet Earth, and that matters. If you had been on the planet Mars, for example, then you would not have experienced this transit because, again, it is a figment of our perspective. Any questions about that? Speaking of Venus, Venus often experiences conjunctions with different objects. And by the way, I probably should define the word conjunction, shouldn't I? Essentially, I'm at the risk of being a little too simplistic. It's when two space bodies appear near each other. But again, that word is important. Appear near each other. So in this picture, this was way back in, 2014. Time flies. So we see here our old North Dome and our old campus above our old projector screen. And I see two bright stars above the projector screen. And of course, those are not stars. Those are planets. Not Jupiter and Saturn. This is Jupiter and Venus. Let's see if you can tell which one is which. Which one's Venus and which one's Jupiter? What do you guys think? You tell me. I'm going to wait for you to answer. Let's zoom in a bit so you can appreciate this a little more. There you go. All right, tell me, which one's Venus and which one's Jupiter? What do you think? You can guess. You have a 50% chance of being correct in your guess. Jupiter is brighter. No, incorrect. So Jupiter normally is brighter in the case of other planets. So for example, Jupiter's brighter than Saturn. But Venus is famously the brightest planet. And so Venus there on the left, yes, very good. Venus is the brighter one and Jupiter's dimmer. By the way, it's impressive when Jupiter and Venus have a conjunction because they are the brightest two planets. So it's cool when you see them. Now, wonderful question. Someone asked, is it brighter because it's closer? That is one of the two reasons that Venus is such a bright planet. Let me show you a picture of Venus. Venus is famous for her high albedo. Albedo is the astronomical term for reflectivity. And the reason that Venus is so reflective is because of her thick clouds, which are very high in altitude, very shiny. This makes Venus reflect a lot of sunlight. Of course, planets do not give off light. That matters a lot when we're talking about what we're discussing now. They only reflect light, and so you see them because of sunlight. Her reflectivity combined with the fact that she's close to us, we're close to her, however you want to say that, make Venus brighter. Now, this is an interesting topic because Jupiter is enormously larger than Venus. You could fit over 1,000 Venuses in Jupiter, and yet Jupiter appears dimmer because he's so much farther away. Over 400 million miles, in fact. So yeah, this is a conjunction of Jupiter and Venus, and this occurred on August of 2014. Now, let me show you another one. This is a view through a telescope. Now, this is a big deal. This is similar to what we're going to experience at the end of this month with Jupiter and Saturn. In this picture, this is a real picture I took back in, what year was it again? 2015, June. We can clearly see Jupiter and Venus, and incredibly, this is the same exposure. Now, Jupiter is he's a king of the planets, Zeus, and Venus is female, Aphrodite in Greek. So, yeah, look at this. You could see Jupiter on the top and Venus in the bottom. This was in the same field of view. This was on a full-frame camera sensor using, I think it was a 700-millimeter telescope. I did some cropping, so it's not a completely accurate representation of the field of view, but it was quite astonishing to see two worlds in the same telescope eyepiece. That is certainly a rare event, and you will have an opportunity to do that at the end of this month with Jupiter and Saturn. Now, what's cool about this picture is You know that Venus is tiny compared to Jupiter. Actually, you know what? Let me prove that real quick. This is a picture of Venus in radar, by the way, without her clouds. So let's get my head out of the way. This is a scale-accurate drawing of our solar system. This is size scale, not distance scale. Please do not be confused. I'm going to zoom in here. And clearly, mighty Jupiter, king of planets, is much bigger than Venus or Earth. And by the way, since we're talking about it, also a bit bigger than Saturn. Although the rings make Saturn look bigger, but that's cheating, right? So yeah, look how tiny Venus is compared to Jupiter. And yet, in my picture, Venus is actually larger than Jupiter. Now, this is kind of common sense. Why is that? Why is it that Venus appears larger than Jupiter in this photograph that I took? What do you think? I'm watching the chat. Why does Jupiter look bigger? Oh, excuse me, smaller in this case. A planet that is significantly smaller than Jupiter looks bigger than Jupiter. Why? Come on, answer the question. I know you know the answer. It's super simple. It's common sense. Come on. Is closer. Yes, that's right. Yeah. So Venus is much, much closer than Jupiter, and so it appears bigger. That's an interesting, again, lesson in perspective, isn't it? Very big things can appear small if they're far away. And this is extremely true in the case of things like stars, which include stars that are much bigger than our sun, which is not exactly small. Back to that image of our solar system to scale, that great bright hemisphere of light on the left-hand side of the screen is the sun, which again makes everything in our solar system look teeny-weeny. And yet the sun is pretty small when you look at it in the sky. Similar in size, apparent size to the moon. Not exactly the same, that's a popular myth, but they look similar in size because, again, of distance. And when you look at stars, distant stars, they look like little specks, again, because so far away. Yeah. I have more to say. Let's see, I'm looking at questions. Someone's explaining angular size. So we often measure things in degrees. And the Earth's moon is famously about half a degree across. So that helps you visualize things a bit. If Earth's moon is half of a degree across, you might be impressed to know that Jupiter and Saturn will appear about 1/10 of a degree apart, much smaller than the diameter of a full moon. And if you want to visualize that, it's about the size of a dime held at arm's length. That's what I've heard. I haven't proven that, but I've heard that enough on the internet. I think it might be true, but something small like that held at arm's length. Good question. So, I'd like to address some hyperbole involving this event, but first I want to keep going on Venus for a second. So here is, get my head out of the way. Here is a picture of the moon, Earth's moon, of course. The planet Jupiter over here, and then above, Saturn. Let's shrink that a bit. So Saturn, Moon, and Jupiter, and this was in August of this year. I may have mentioned earlier, this event has been playing out for the entire year. And if you haven't been paying attention, these two have been together, so to speak, in the sky for quite a while now. And so you can actually notice that there's been quite a change in the last few months. For example, this is time-lapse. This was a few nights ago. And there's Jupiter. And there's Saturn. Look how much closer they are now. See that? What a difference a few months make. I'm going to let this run for a second. Now, I shot this time-lapse because I was hoping to get the pair of them moving behind Mount Hood. That did not occur. Aren't they motion blurred in that picture? Aren't they? Well, motion blur is caused by the long exposure of the camera. So it's a dark night, poor seeing conditions because of moisture in the air. It's wintertime, it was foggy. And so the reason there's a blur, so to speak, is because the camera, in this case, was performing 10-second exposures. So 10 seconds of light gathering gives you a little bit of a streak. And you can tell that from the airplanes. Those streaks zipping by our airplanes, and they look elongated because in 10 seconds they moved that much. Yeah. Good question. I'm going to pause this. I want you to notice something. This is pretty cool. This is only a 250 millimeter lens. This is the lens I used to shoot this. 250 millimeters is not that long. It's telephoto, but it's not super long like a telescope. And yeah, even at only 250 millimeters, what do we see? The moons. So we have the bright thing here. Where's my mouse? So there's Jupiter, and then we see two of its moons, Ganymede and I believe Europa. And then we see Saturn, and that little dot next to it is Saturn's moon Titan. And the reason I wanted to point out the moons is because it's been indicated that Saturn will actually appear as close to Jupiter in the sky as one of its moons, Ganymede. So that helps you visualize just how close the two are going to be. You will be able to split them. You won't need a telescope to split them. But with a telescope, you will be rewarded with actual details. You will see features. Now, as the two converge, let's talk about hype for a second. Let's talk about myths for a second. There seems to be this opinion that as the two, let's say, converge on each other, as they close on each other, somehow, magically, their luminosity is going to increase until they get so close that you're going to need goggles to view them safely. You're going to be blinded by the bright light of the Christmas star. I want you to know this is ridiculous. You don't need your nuclear safety goggles to observe the conjunction of Jupiter and Saturn, because they are certainly not going to magically, massively increase each other's brightness. Are there any questions about that? I'm sorry if that disappoints you. I know a lot of people thought they were going to see this dazzling beacon in the sky. I'm going to pause it again. Let me go back a few frames. Oops. By the way, just for funsies, since I brought it up, these are all airplanes. This is an airplane, this is an airplane, this is an airplane, but this is actually a delivery vehicle for a Starlink satellite, so that's fun. Not everything you see in the sky is an airplane. Many of the objects you see are satellites or rocket bodies, so there you go, there's some fun. Okay, I have a lot more to say, but any questions so far? Would the view that you were looking at be different in other parts of the world? That's a very good question. Yes, the good news is you can see it wherever you are in the world. It would just be higher or lower, depending on your latitude. The time of year might be more conducive to viewing. For example, if you're in the southern hemisphere, this is getting close to summertime, and summer is a better time in terms of weather in many places. And by the way, speaking of weather, I want to repeat this. This is why I think it's an important thing that you try multiple nights to observe this event as it unfolds, because in December it's often cloudy. For example, it's cloudy right now. I was actually hoping to show these two objects in the sky together live. They are close enough that with one of our telescopes I can get them together, but I couldn't because it's literally snowing. That could be happening on the 21st of December. It wouldn't surprise me at all, actually. So try. Again, if you live in a different hemisphere, different latitude, you might have better weather. So, yeah. But yeah, it will affect how high they appear. This is true of anything in the sky, isn't it? Yeah. That's a good question. Are you planning on hosting anything on the 21st? Yes. I'm going to try to just do a little special thing. I don't know about a show. We'll figure that out in the next week. It's not a big deal, but hopefully, if the weather allows it, I'm going to try to provide a live stream of the actual two objects in the sky. Stay tuned for that. You'll be seeing some announcements if we do it. Right now, it's not a concrete thing, but it would be cool if we could broadcast it live. We have the technology to do it. It's just whether or not Mother Nature allows it. Yeah. Okay. Now, I mentioned that Christmas star thing and this idea that this is going to be this dazzling beacon in the night, and that, again, these two objects are going to magically increase in luminosity. They will not, although people may have interpreted the two objects becoming very close as significant in the old days. For example, good old Kepler, Johannes Kepler, back in the year, what year was that, 1603, he calculated that there would have been a great conjunction of Jupiter and Saturn in the year 7 BC, and he thought, oh, perhaps that was the famous star of Bethlehem. I don't know. I don't know that people would have interpreted two objects as close together as a single bright object, but maybe. Kepler was very interested in these conjunctions, and he charted their positions, and he noticed something. He noticed that there was this shifting of the dates and positions. This is essentially the zodiac or the plane of the ecliptic, and the planets move through the plane of the ecliptic, and he noticed that there was this shift in the location on the sky where the conjunction occurred. And the reason that shift occurs is because there is no synchronization at work. The Earth's orbit is not synchronized to Jupiter. Jupiter's is not synchronized to Saturn, although Jupiter and Saturn do enjoy an almost orbital resonance, but not quite. So their orbits affect each other, but in the case of Jupiter and Earth, or Saturn and Earth, our Earth goes around the sun at a rate that is not linked to their orbital velocity, and so the position, so to speak, in the sky of these events changes over time. By the way, there's a quality difference of these events as well, and there are better and worse conjunctions. You may have heard that this is the best example of one of these conjunctions in 800 years. That is incorrect, although it is the best since the year, what was it, 1623. So this is the best example of this conjunction since then. However, I would not describe a great conjunction as a once-in-a-lifetime event. They happen roughly every 20 years. If you don't believe me, let me show you. By the way, this little animation is about to explain to you what is going on. This is the reason that conjunctions occur. As we've already discussed, Jupiter and Saturn are, of course, nowhere near each other, but they appear so because of where they are and where we are. So let me get my head out of the way here. Let's play this video. So look, 2000, we had a great conjunction. Oh, this is the one's coming up, 2020, great conjunction. October 2040, another great conjunction. That's nice. And another one in April 2060. How exciting. And another one, 2080, March. Look at that. Now, what's interesting about this particular collection of conjunctions is they're all kind of inconvenient. Because you'll notice our line of sight across both planets is very near to the sun. And this means that they will appear near to the sun, which means they're either going to appear low in twilight or in the sunset light, or low in the east, rising before sunrise. In either case, that's bad news because they're going to be low and as a result obscured by the atmosphere. Some of you might remember I had a video last week of the star Sirius twinkling. Twinkling is not a real phenomenon, of course, but it's caused by Earth's atmosphere. Stars twinkle because of the air you're looking through. Air is not a perfectly translucent medium. It moves, it changes shape, it's amorphous. The rays of light are constantly shifted. This is very inconvenient. It makes science more difficult. Now, on this subject, you may have heard that planets don't twinkle. There is some truth to that. If you look at Jupiter in the sky next to a bright star, you'll notice that Jupiter seems a lot more steady than the star is. However, if you were to magnify Jupiter or Saturn in a telescope, unfortunately, you would find that they are not indeed sharp images. You're not going to see something like this. You're not even going to see something like that. What you're going to see is something that resembles that, wobbling and wiggling in the atmosphere. Planets appear to twinkle less than stars, essentially, because there's more surface area at play. Stars are so far away that they represent an infinitesimal speck, and so that light is easily disrupted by the air, but planets hold up a little bit better. So this is another reason why I don't want you to wait till the 21st to observe this conjunction, because even if the weather allows you to observe it, those two planets are going to be hiding behind about 1,000 miles of atmosphere, and that air will wreak havoc on your viewing conditions. We always like to view an object in space when it's as high as possible, because the higher it is in the sky, the less air you're looking through. Any questions about that? Message retracted. I didn't know you could do that. Let's see. Were these events ever considered frightening? Oh yeah, people love to read way too much into everything. And I can tell you a story. By the way, this is not off topic at all. In the last few weeks, I've received multiple emails and phone calls about this, and people ask questions like, "What does it mean?" As if some form of doom is approaching, as if it's always implied that any astronomical event in the sky implies either doom or something positive, but either way, it implies something. In reality, it implies that you were in the right place at the right time to observe this apparition. That's a good word to use when you're describing these events, because they're not really events. It's a matter of perspective. That image I showed you of the Venus-Jupiter conjunction a few years ago, that was especially popular with people who thought it was some kind of omen. Just randomly, here's a picture of Venus and the Moon. These are conjunctions that happen frequently. And yeah, always pretty though, always worth seeing. You may have seen this in the time-lapse of the countdown video. So I forgot to ask this question earlier, but it's kind of related to what we're talking about right now. Why is it that Venus conjunctions are so much more common than Jupiter or Saturn conjunctions, or in this case, great conjunctions? I want to see if you can tell me. Why is it that Venus conjunctions occur so much more often? Tell me. I'm reading the chat. Took a Jupiter, sparkling with blue. Someone's pointing out that Jupiter looked like it was sparkling with blue light. That's caused by atmospheric scintillation and also something known as chromatic aberration, caused by the glass in the camera lens you're using. Glass does not slow all wavelengths of light uniformly, and it creates this undesirable artifact known as chromatic aberration. That could be why Jupiter looked blue, or it's also, for example, it also looks yellow. Our big refracting telescope here at the observatory, it's an old achromat. It doesn't have corrective optics for color, and so it will often reveal Jupiter as kind of yellow, and that's a false color created by the optics, the glass itself. So the combination of Earth's atmospheric scintillation and the chromatic aberration of glass means that when you look at a bright, high-contrast object like Venus or Jupiter, yes, the colors will often look false. Yeah, that's true of twinkling stars as well. Yeah. All right, so I asked the question. Well, that's an interesting answer. I said, why is it that Venus transits happen more often? And someone says because we're closer to Venus. That's true, but then there's something else. Venus is literally faster, so she comes and goes and comes and goes more often, and she passes by objects in the sky more often as a result. That's a good observation. So on that subject, let's prove it. I'm going to put up a simulation of the sky. Hold that thought. All right, now watch this. This is going to be fun. Okay, this is a software program I like to use a lot called Solar System Scope, and we have here a nice accurate simulation of our solar system right now. This is right now tonight at this time. This is updated every minute. Now, there's sun there is in the middle, of course, Mercury, Venus, Earth, Mars. We zoom out a bit. We have Jupiter and Saturn, farther, Uranus, Neptune. Now, I'm going to do something I ordinarily never do with this software. I am going to exaggerate the sizes of the planets so that you can see them more clearly. I want to repeat, this is an exaggeration, this is not accurate. So here we go. Now we have ridiculously, and by the way, also inconsistently, increased the size of the planets. And now they look like marbles that are all attractive and detailed. The sizes are completely ridiculous. For example, let's see here, I don't know where to start. Let's go over here to Jupiter. Jupiter is about the same size as the Sun. Of course, that's wrong. Earth and Mars are not that different. Venus and Earth are the same. That's right. That's good. Mercury's way too big. I could go on and on. But so let's go to now, and I want you to see something. Let's go over here. Let's speed up time in the inner solar system first. Of course, who's the fastest planet? You should be able to tell me not just by watching, but also by knowing. It's common knowledge. What's the fastest planet, guys? Tell me. Someone type it. Who's the fastest planet? I hope we're not delayed. I'm always bragging about the low latency of YouTube Live. I hope. Very good. So Mercury is the fastest planet. Why must he be? Tell me. Why must Mercury be so fast? What would happen to him if he slowed down? I'm watching the chat. Okay, Mercury, yes. Why does he have to go so fast? What would happen if he slowed down? I guess I'm not going to get the answer, so I'll just tell you. Oh, it fell into the sun. Yeah, that's right. So because Mercury is close to the sun, it experiences stronger gravity, and of course, if Mercury slowed down, in he would go. This is also true of Venus when compared to Earth. Notice she is faster than us. Venus's year is only 225 days, guys. So this is one of the reasons why she has more conjunctions. Let's try to simulate a conjunction. I'm not planning this. I'm just going to do it. I'm just going to do this totally randomly. So let's slow down time a bit. So I'm watching this. Now that's interesting right there. See that? So if I back up a little bit. So that would be an Venus-Mercury conjunction. See that? If you got up in the morning, let's see, yes, that's right. If you got up in the morning, you'd see Mercury and Venus close to each other, even though, of course, they are not close to each other. Yeah. So we just, what year is this? What is the month? What is the time right now? January 2038. There you go. We just predicted the future. I bet you it's right. By the way, one of the fun things about astronomy is you can actually, with some confidence, predict the future. Does that make you feel powerful? Using a modern computer that might be sitting on your desk, you can do these simulations out for tens of thousands, even hundreds of thousands of years. Okay, so let's back out here. Let's go back to now. As you can see, we have Saturn and Jupiter, and then Earth almost in a line. Let's go into the future, just a few days. Okay, now we're getting close to the 21st. Okay, it's now the 21st. And look at this. We got a nice laser beam going on here. Earth, Jupiter, Saturn. But again, inconvenient because they are to the left of the sun. They will appear low right after sunset. Now let's prove our ability to predict the future by predicting the past and seeing if it's accurate. Let's go back in time to the year 2020. Oh wait, that's wrong. The year 2000 rather. Notice the motions here. Notice how they're no longer, quote, near each other. It's now the year 2012. It's now the year 2006, 2005, 2004, 2003, 2001. Okay, it's now the year 2000. Now, it seems that Earth is not quite right positioned. There's Earth right there. There's Jupiter and Saturn. Let's increase. Let's go forward. No, let's go backwards in time, actually. And look at that. In June 2000, we got, again, that nice laser beam conjunction. Again, I hope we understand that these objects are not close to each other in any means. By any means, it's simply that we are in the right place to make them appear that they are. Yeah. All right, questions. Let's see. Someone asked a great question about the time it took. I'm actually going to provide a very accurate answer for that in a second. Is the Earth technically faster than Mercury? Is it just relative to the Sun that Mercury is? No, Mercury actually does have a significantly faster orbital velocity. Something like 20,000 miles an hour faster. So let's what was that? I don't think I need to do another simulation, although I could. Instead, I'm actually going to do not constant, all orbits are elliptical. Yeah, and by the way, this software is simulating the fact that the orbits are elliptical. Now, on that subject, orbits are also not flat. The orbits are similar, but they're not exact. Our solar system contains something we call the ecliptic plane. It's an imaginary plane that projects our orbit into the sky. We find that the heavy objects roughly adhere to it, but not exactly, because all the orbits in our solar system are crooked, or inclined, and also eccentric, which is how off-center they are. As a result, every conjunction is different, and these things do not happen like clockwork. Even though you might have one every 20 years, it will appear differently. I mentioned that in the year 1623, there was a really good one. This year is another good one. But there's an even better one coming. In the year 7541, there will be a great conjunction of Jupiter and Saturn that is so great that Jupiter will actually occult Saturn, which means Jupiter will actually pass in front of Saturn directly. So that's even better than appearing close to each other, isn't it? Yeah, don't wait for that. That's a long time from now. That's 5,500 years from now. Yeah. What does it mean? I know he's joking, so I'm not going to attack him for that. Let's see here. I'm looking at questions. I have a picture of something transiting the moon. I could never figure out what it was. It was probably the International Space Station or a satellite. I've actually seen that before myself. Let me do a little. Let me see if I have it handy. I might. If I don't, I will skip this topic. But I don't think I have it handy. But yeah, there are lots of videos on the internet of things going in front of the moon, including the International Space Station. So back to my main show, Great Conjunction Talk. I want to show you now this same kind of simulation, but from the perspective of Earth. Okay, so this is the sky. I'm going to pause time. Okay, this is Goldendale right now. And if you look over here in the southwest, oh, they've already set. It's 7:35. There they are, Saturn and Jupiter. Let's back up a few hours. I'm going to turn the atmosphere on. Watch this. I'm going to do a little ground simulation here. Okay, atmosphere simulation is on. Now, I'm going to jump ahead a few days. Watch what happens. Oh, there's the, well, it's going to be beautiful. What day is that? So on the 16th, so just 3 days, you're going to see a crescent moon right next to the two. The next day, even bigger crescent moon. That'll be cool. So the 17th, 18th, 19th, 20th, 21st. There it is, the closest conjunction. But again, notice it's in the glow of twilight and it's quite low. So once again, I'm going to repeat myself. Get out there and see this while you can. There's no guarantee you'll see it after on the day in question. Now, speaking of after, though, watch this. I'm going to turn the ground off. I'm going to turn the atmosphere off. I'm going to lock onto Jupiter here. I'm going to increase speed a bit. Watch this. Okay, so the pair, Jupiter and Saturn, will go behind the Sun on 28th of January and then pop out on the other side right after that. Looks like in March or maybe late February, you'll be able to see them pretty well together. Jupiter, oh, there's Mercury and Saturn. They won't be as close as they were, but the difference is now they're going to be on the early morning side, so you're going to have to get up early in the morning if you want to see them. I just want to make it clear that you don't need to feel bad if you miss the exact moment of conjunction because you have plenty of stuff to see before and after it. Any questions about that? Now, I want to answer a really good question that I enjoyed. I saw a question that brought joy to my head because I love answering it. Someone asked about the time delay. So let's do it right now. Let's go back in time just a few hours so they're actually up. There they are. Okay. All right, Jupiter, right now is at a distance of 5.8, actually 5.9 astronomical units. Now, some of you might remember from a previous show what an astronomical unit is. It's the average distance between Earth and Sun. Some of you might know from grade school that it takes roughly 8 minutes for light to traverse 1 AU. So let's do the math. Let's move my calculator up so it's not behind my head. Really? Did that just happen? I just stretched my calculator. Look how long it is. There you go. That's better. Actually, I'll put it over here. So I'm going to multiply, what was it? 5.9 AUs by 8 minutes. So it takes 47 minutes for the light to reach us from Jupiter right now. Now, let's see if you guys can tell me. Why don't I just memorize that? Why would I have to do the math just now like I did? Why don't I just memorize that and use it as a tool in my job? Someone tell me. Why did I have to do the math just now? Someone say. Let's see if you can figure it out. Why did I have to use a calculator to figure that out? Why didn't I just memorize it from a book? Watch in the chat. Distance is always changing. That's right. Distance from us varies. Very good. So the reason the distance changes is because we orbit the Sun at a certain speed. Jupiter orbits the Sun at a certain speed. Our orbits are inclined, eccentric ellipses. So the distance is always changing. Now, let's continue answering the question about the time delay. Let's go into the future to the 21st. Okay, there it is. Check it out. That's how they're going to look. Check it out, guys, in a telescope. Jupiter and Saturn together. Now, Jupiter's distance is about the same. I'm not going to bother recalculating that, but let's look at Saturn's distance. So to Saturn, 10.8 AUs. 10.8 astronomical units multiplied by 8 minutes. Oh, look at that, 86 minutes. So what, an hour and 16 minutes? Is it wrong? 26 minutes, an hour and 20, so almost an hour and a half. That's a much greater time delay, isn't it? Because, of course, Saturn is farther away. Yeah, so that's another lesson in perspective, isn't it? It's not just determined by your location, it's also determined by the speed of light itself, which, of course, is not instantaneous, and the object's distance or its proximity will determine how far back in time you're looking. So that actually complicates the concept of a conjunction, because it's not just about position, it's also about time itself. Imagine that. Okay, questions. So my friend Tom Palakis, who's an astronomer in Arizona, I hope he's watching, he made something cool. Check this out. This is a simulation. He took pictures of Jupiter and Saturn last night. These are real pictures that he took with his telescope. And then he composited the two pictures together based on the positions of the two bodies on the 21st. So this is a simulation, although the images are real. There's something else that we often fail to acknowledge when it comes to trying to image events like this or view them through a telescope, and that is that the brightness of the two bodies is quite different. In the case of Jupiter, it's much brighter than the planet Saturn, because closer, also shinier. So then in the next picture, he actually increased the brightness of Saturn artificially so they appeared similar. You're probably going to see a lot of pictures on the internet that look kind of like this one, although they're going to be of much lower quality most likely, because he took these pictures last week, or yesterday, whereas the images that we take on the 21st will probably be flawed because you're going to be looking through a lot more atmosphere. I hate to say it, I don't want to discourage you, but it wouldn't surprise me if the two planets appear as amorphous blobs. Saturn will be vaguely recognizable as an oval, and Jupiter will be a big circle. Yeah. And of course, you'll also most likely be able to see the moons if you look through a telescope. Questions about that? Their lunar planes are so out of parallel. Why? That's a good question. Well, the reason the lunar planes of the two planets are so out of parallel is because they're not related to each other. Different planets have different obliquities. That's a good question. Hold that thought. So here we see obliquity of some different planets. As you can see, Jupiter's obliquity is only 3 degrees, so he's not that crooked. But then look at Saturn, 27 degrees, more crooked than Earth. The major moons that orbit these two worlds tend to agree with the obliquity of their equator. So the equators of both of these planets are orbited by their largest, most massive moons. And so that's why the moon planes appear crooked, because they literally are. There is no up in outer space, is there? By the way, since I brought this graphic up, I want to make it clear the reason I drew the boxes around these four sets, or these two sets, is so you understand that this is one scale factor, and this is another scale factor. Earth is not the same size as Saturn. Of course, I shouldn't have to explain that, but whenever I use a graphic like this, I have to be careful because people jump to that conclusion. So yeah, there's one scale factor at work in this box, and there's another scale factor at work in this box. All right. Hold that thought. So back to this picture here. Any questions about what hopefully looks kind of like this in your telescope when you look on the 21st? Any questions at all, anything like this? Questions. I have a few more things to say. I think I might actually do what I said I would do finally, and actually end up being on time, or ending up a little short. I have a few more things to say, but let's get another question going. Let's see, and then I'm gonna. Actually, I have some questions here. Let's see. Does this linear alignment relative to Earth have any conceivable gravitational anomaly? Nothing that we could measure, and certainly nothing that's going to cause doomsday. I bring that up because I've read stories about a number of hoaxes that have been perpetrated over the last century. So these are modern hoaxes. Once we became very good at predicting the positions of things, there was this idea that planetary alignments would create these sort of gravitational doom beams, and the planets would rip each other out of their orbits and go fleeing out of space. And no, that ain't going to happen. You're fine, trust me. Of course, mighty planets like Jupiter have tremendous gravitational influence, but in his case, he's over 400 million miles away. If you wanted to be flung from your orbit by Jupiter, we need to be a lot closer to him. And of course, we do that deliberately, don't we? Our spacecraft have often used Jupiter and also sometimes Saturn to make major course corrections, taking advantage of the incredible ability of big planets to divert objects with their mighty gravity. That's a great segue into a topic I wanted to discuss. People are often impressed by the fact that things like conjunctions and occultations and transits and eclipses are possible because it seems so unlikely that objects could come anywhere near each other. When you think of space, you often think of objects whizzing all over the place. But in fact, when it comes to the major bodies of our solar system, there is a planar distribution of mass, and I believe we brought it up earlier, the ecliptic plane. Before I get into that more, I want to show you something from last week. Hold that thought. Where is my 3D universe? Oh, there it is. So I showed you a video of the mapping ability of a famous astrometric telescope called Gaia, and I mentioned the fact that it can map things beyond just stars. Check it out. So this is a map produced by Gaia of a number of asteroids, thousands of them actually. And what you'll notice is that the asteroids do not adhere to the ecliptic plane. They're all over the place. This is even more so true in the case of comets. Comets often have even wilder orbits than asteroids. Not only will they be significantly inclined on the ecliptic, they will often be extremely eccentric, meaning very off-center compared to the sun. So our solar system is not so neat and tidy. It is not so uniformly distributed in a planar fashion when it comes to minor bodies. And that's because minor bodies are easily disrupted by major bodies like planets. Yeah. So, speaking of major bodies. Hold that thought. I'm going to go back onto the simulation of the sky here. And I'm going to draw the ecliptic plane onto the screen. Okay, that yellow or orange line there, that's the plane of the ecliptic. Notice that Jupiter and Saturn are actually below it, but they're not that far. Let's lock onto Saturn specifically here. Going into the future. Saturn seems to be staying below the ecliptic plane. There goes the sun. That was kind of impressive. Let's go a little faster. Oh, it just went retrograde. No, it's not because of our motion. Now it's getting farther from the plane of the ecliptic. Saturn's still below it. Let's go a little faster into the future. Oh, there. Oh, now Saturn's above the plane of the ecliptic. What year is that? In the year 2036. The reason it seems to deviate from the plane, in this case now above it, is because, again, everything's crooked. Earth's orbit and its inclination do not agree with Saturn's orbit or its inclination. So we see this shifting of position. Notice how Saturn seems to be zigzagging. That is retrograde motion, which is not actually just a magical, mystical thing. Retrograde motion is an actual apparent reversing of course, caused again by that good old perspective. And it's not so much that Saturn's doing anything different. It's because we are, so to speak, going between Saturn and the sun. Earth's motion creates that zigzag effect. And of course, everything does that, not just Saturn in our solar system. But that zigzag effect is what does create the actual, real manifestation of retrograde, as opposed to prograde. Everything in our solar system, with a very short list of exceptions, moves in a prograde manner. This is not a tangent. There's something I want to show you. There's a reason why the major bodies of our solar system adhere to an ecliptic plane, or roughly do so. Keep watching that fun animation while I bring this back up. So this is a very impressive real picture. All right, this is real. This is an actual image of a star system called HL Tauri. This is a baby star system. You know what? Before I continue, let's slow that thing down. Let's go back to now. There you go. That's a little happier there. All right, as I was saying. Oh, that's fast. HL Tauri is a baby star system that is extraordinary because not only do we see the baby star or protostar in the center, we see that it's surrounded by an accretion disk which has grooves carved into it. And those grooves contain planetesimals or baby planets. These baby planets are accreting mass from the disk, and that's why those grooves exist. So we're seeing the birth of a new star system with baby planets before our very eyes. This is not unique, but this is one of the most impressive pictures of one. Now, our own solar system would have looked something like this about 4.5 billion years ago. And the reason that the material settles into a disk or a plane is because of that famous pseudo force known as centrifugal force. Centrifugal force is not a force of nature, it is a manifestation of inertia. As an object rotates, the most efficient position for material to take will be somewhere on a two-dimensional plane, and that's where the material wants to be. Now, if you were to release it, the material would fly off into space wherever it wanted to go at the moment you released it. But the material is being restrained by a true force of nature, gravity, Gravity pulls in on the material, while centrifugal force seems to want to pull it out. By the way, gravity manifests centripetal, not centrifugal, centripetal force. So gravity pulls in as a centripetal actor. Inertia tries to carry things away as a centrifugal actor. Those are two different words. Yeah. So the reason that bodies in our solar system roughly adhere to a plane is because that's where they were born. That's also why they mostly go the same direction. Again, the word is prograde. They move in a prograde manner because they retain the inertia of their birth. Any object in our solar system that moves in a retrograde manner, a true retrograde manner, not an illusory run created by our perspective, but a true backwards motion, that object will probably do so because it was perturbed by another body. Probably the most famous retrograde object in our solar system is Neptune's moon Triton, not to be confused with Saturn's moon Titan. Triton has a backwards orbit. Triton is likely a captured dwarf planet. So Neptune captured this body in such a way that it ended up going the wrong way around Neptune. I think that's quite interesting. Interestingly, it doesn't differentiate much from the plane, but it does differentiate in that it goes the wrong direction. I think that's neat. Any questions about that? That's a deep topic. The reason we can have conjunctions still to this day is because space bodies, major bodies, retain the inertia and the relative rough placement of their birth. It's true that planets migrate. We know that most of the planets have moved from their birthplace, but they moved within the plane of that disk. Questions about that? Oh, that's a good question. Someone points out Moon's gravitational influence is so much stronger than Jupiter and Saturn combined. Of course it is, because it's so close. You know what a good example of that is tides. You know, there's two tides. You got lunar tides and you have solar tides. The sun creates tides and the moon does. Of course, the sun is enormously heavier than the moon, but its tides are weaker because the moon is so much closer. The sun is so much farther away, obviously. Yeah. Good. That was a good observation. Oh, I see a popular myth. Oh, I love dispelling myths. So someone pointed out the truth, the fact that Jupiter shields us, that it protects us. Au contraire, we used to think that. But with supercomputer analysis of literally millions of orbits of both asteroids and comets, we discovered that yes, even though the giant planets do gobble up or capture bodies, they also destabilize the orbits of bodies, sending them careening into the inner solar system. So it might be a wash, and if it's not a wash, it's probably closer to the mayhem than it is to the protection. It's likely that the giant planets barrage us with material objects that they disrupt from their ordinarily relatively stable orbits. Jupiter and Saturn are truly a massive influence on minor bodies because they are physically massive bodies. Yeah, that's a good topic. So yeah, I also was taught that in school, that the gas giants protect the inner planets, but now we see, they might actually be throwing things at us, which is not helpful. Thanks, guys. Yeah. The good news is for all of us is that we live in a relatively peaceful period in the history of our solar system. We know that our solar system used to be a much more violent place, and we referred to that violent period as the heavy bombardment period. Very likely that part of the reason the heavy bombardment period was so violent is because planets were dislodging minor bodies left and right. We know that Jupiter and Saturn, for example, used to be much closer to the sun. For all we know, they destroyed entire worlds. We don't know how many planets were flung out or thrown into the sun or eaten by Jupiter and Saturn in the early days of our solar system. Our solar system used to be an extremely chaotic place. And I often like to use the example of the planet Mercury. Planet Mercury is utterly covered with craters. This is not the moon, this is the planet Mercury. And again, because of heavy bombardment, we're not seeing new craters being added in any kind of regular fashion now. The same is true of Earth's moon. These are essentially a physical record of a much more violent period in our ancient past. Earth has its share of craters as well, although we have an active living world with plate tectonics and continental drift, erosion, which are raised craters. Also, we have a thick atmosphere that protects us from small bodies. Yeah. Speaking of protection, you live on a planet with lots of protections. So you have the atmosphere, which causes most things to burn up, and then you also have Earth's electromagnetic field, which protects the atmosphere from solar wind ablation. The sun is always stripping planets of their atmospheres. So, yeah, if you want to talk about things protecting you, be grateful for this wonderful planet Earth that you inhabit. Questions? I'm looking at the chat right now. I'm going to put up a useful video just because it was... Actually, no, let's just do this one. Let's do something decorative. This is that time lapse of Jupiter and Saturn setting behind the mountain. Now, I have some friends. Does the moon protect us? No. So the moon gets hit less often than Earth. Earth is a big target. We're 4 times larger than the moon, and we're significantly heavier. So Earth does get struck more than the moon. You could think of the Earth perhaps as protecting the moon if you wanted to be silly about it. Yeah. Good old thanks Earth, the moon must say. Yeah. The moon gets clobbered still. So it's not like it's been successful in its protective duties. All right. Can you explain how the electromagnetic field protects us as a planet? Yes, I can. So that's a fun topic. Hold that thought. I used this graphic last week. I hope you don't mind. So the sun is behind my head in this picture. I don't think it matters. The white snow in this picture is solar wind. Now, solar wind is not actually wind. It is a constant barrage of high energy, mostly hydrogen and helium ions, which are being propelled at up to 2 million miles per hour by solar radiation pressure. And this is a very destructive force. It strips planets of their atmospheres. It's the reason that Mercury has no atmosphere whatsoever. It's the reason that Venus has lost all of her lightweight atomic elements, leaving only heavy molecular gases like carbon dioxide. It's the reason that Mars has lost most of his atmosphere. So solar wind is very destructive. Living on a planet with a strong field, as long as Earth's geodynamo continues to operate, we will essentially be protected from solar wind. But this is not forever. Eventually, Earth's core will solidify completely. The geodynamo will collapse, and Earth's atmosphere will be slowly stripped away. The good news for you doomsday fans is that even if it happens tomorrow, it will take hundreds of millions of years for our atmosphere to be stripped, so this is nothing for you to worry about. We witness this on Mars happening as we speak. What little remains of Mars as atmosphere continues to be stripped away, and we've observed this with a space probe, an actual Mars orbiting satellite called MAVEN. And we know that Mars used to have a magnetic field, but we also know that it collapsed. We see remnants of it, but we don't see the actual Mars or Ares dynamo, if you want to make up a word, the geodynamo of Mars producing it. If you don't know how our field works, it's not a permanent magnet. It's also not caused by giant deposits of iron at the poles, which our grandparents were taught. It is because we have an active core, a solid inner iron core surrounded by a molten outer core. The two move and interact and produce essentially a natural generator or dynamo. It is electrical current flowing through the core that produces Earth's magnetic field. Again, it's not an action of permanent magnets. And you couldn't have permanent magnets anyway because of those temperatures. The core is many tens of thousands, or not tens of thousands, it is thousands and thousands of degrees. And you wouldn't be able to have permanent magnets operational at those temperatures. So this is an electromagnetic process. And in this drawing, you can see they've illustrated it. And I want to repeat, this is a drawing. This is not a photograph. Yeah. Okay? Good. All right, I would like to gently and politely start wrapping it up for your benefit. So you can get outside and look at the thing that you probably won't see because of clouds, but you can try anyway. Yeah. So I have some friends in the chat tonight. How does REM repel solar? Well, the charged particles, because they are charged, they're attracted to an electromagnetic field. And so let's continue on that for a second. They will move down the field lines towards the Earth's core and run into the upper atmosphere. By the way, that's how we get the aurora. The northern lights happens because of these particles being drawn down the electromagnetic lines. And that's also what causes, by the way, the Van Allen belts. There's these regions of dangerous radiation above Earth where the magnetic fields have actually trapped that high energy material. So it's not all good. Anyway, and that, by the way, can damage satellites and space missions and be dangerous to humans. So we try not to spend too much time in the Van Allen belts when we're forced to move through them. Some satellites actually work in them, but they're designed to study them. Yeah. Thank you. Oh, you're welcome. Yeah. Hasn't Earth's magnetic south and north? Yes. So there is an acceleration going on, actually, in the movement of Earth's magnetic field. I'm going to hold on to that question for another day because we actually have a whole show about that coming up in a few weeks. So we're going to talk about Earth's magnetic field in great detail, in fact, including the fact that it's in the process of slowly flipping, and also that it's migrating. By the way, once again, doomsday fans, Earth's magnetic field flipping is not going to ruin everything. It would be very interesting, actually, from a scientific standpoint. It would make compasses useless, and it could wreak havoc with some electronics, but it's not going to, I don't know, destroy the world or whatever people think. Pole shifts do happen. On planets, they tend to happen slowly. On the sun, it happens every 11 years. Every 11 years, the sun's magnetic field flips. And by the way, that's what gives us the solar cycle of activity. And you may have heard that the most recent cycles have all been unusually quiet. We haven't seen the sun this quiet in all of modern history. The new solar cycle is starting to wake up, and we have no reason to think it's going to be active, or more active than the last one, but we'll see. So anyway, that's a good question. All right, I'm going to look at my summary here. So I was going to say, I have some friends in the chat who had some ideas about what to talk about. Remind me if I missed anything. I think it's an important topic. I think we hopefully learned a few things, and I hope we dispelled some myths. But yeah, friends of mine or people that are volunteering, feel free to throw out some topics of discussion. We're going to start wrapping it up. Okay, let's see what we got. We did really well on the questions tonight. We answered a lot. Let's see. Looking at questions. If we had many retrograde objects, wouldn't there be lots of collisions? No, maybe not. We discovered that Saturn has a retrograde moon that's moving along the moon plane with other prograde moons, so it seems to be lucking out so far. So, I don't know. You don't necessarily expect collisions because space is big and empty. Even objects that are close to each other can still miss by many, many thousands or millions of miles. Yeah. Collisions are actually kind of hard. When it comes to space bodies, especially little ones, collisions are very unlikely. The only objects that experience really constant collisions are very big, heavy objects, essentially big, heavy targets. Yeah. Are you able to take pictures of planets at Goldendale Observatory or the moon? Oh, yeah, I take tons of pictures. A lot of the stuff you've seen tonight, we shot here. We've planned to dramatically improve that capability in the future over the coming months and years. We're buying some new hardware. We're trying to move away from the whole folksy junk donated material that kind of works and kind of doesn't, and is held together with duct tape and baling wire. I've been trying to encourage use of good material, good equipment, and some of the upgrades we're making are intended specifically for imaging. So yeah, the answer is yes. We take pictures like that, and we plan to take much better ones over the coming months and years. Thanks for asking. Imaging is very important. It's a great way to convey information, isn't it? I mean, it's hard to show people what's in an eyepiece of a telescope, especially if they're thousands of miles away. But with stuff like this, technology like this, we can, of course, display images and videos, like the one you're watching. This is time-lapse, yeah. All right, let's see. Are you looking forward for a trip into space, visit to Jupiter? I guarantee it with complete confidence I will never visit Jupiter, although I would love to imagine that when I'm an old man, I can buy a ticket to the moon and go there and look at Earth through a telescope. I always thought when I was a little kid that would be easy. At some point in my life, I'd be able to go to the moon and look at the Earth through a telescope. I hope that happens, and if it's not me, I hope someone gets to do it. And there is interest in returning to the moon, and you may have heard China is working on it right now as we speak. They're actively bringing samples back. The first time we've had a sample return mission since the 1970s from the moon. That's pretty cool. So yeah, I would love to go to the moon, but not Jupiter because it's a long trip and a dangerous trip, and I don't even know why we would bother. I think that robots are better suited for exploring the outer solar system for many, many, many reasons, including cost, but not limited to cost. Yeah. All right, good. In the Starship, maybe in the next 10, 20 years. Yeah, maybe. That would be cool. I'm cautiously optimistic. But even if I don't get to do it, I just hope someone does. I think we should put a webcam on the moon. I call it the Lunar Webcam Project. That's what I want to do. Where you can just look at, specifically not to look at the moon, but to look back at the Earth. I think that's kind of profound. A very short transmission delay. It'd be easy to keep in touch with a camera on the moon. You just got to make sure it can survive the long, cold lunar night. Yep. All right, questions about the conjunction. Oh yeah, I forgot. So something to end the show on. There's another natural event going on right now. Let's see if you know. Let's see if anyone knows. And, this is something that happens every year. That's a hint. Anybody know what's happening right now, actually tonight, unrelated to the Jupiter thing? Let's see if you know. I'm watching the chat. A natural event. Yes, good. The Geminids. So the Geminid meteor shower is becoming, I'll tell you a story. The Geminids are becoming my favorite meteor shower. Everyone is supposed to say that the Perseids are their favorite because they're the best. But there's something unique about the Geminid meteor showers. It's resultant from a rock comet known as 3200 Phaeton. It's either an icy asteroid or a rocky comet. But either way, because it's so rocky, the material left behind is full of heavy elements, minerals, metals, things like that. As a result, the Geminids produce a lot of fireballs, including ones that will leave a tail. Watch this. This is a one-to-one crop of a time lapse I did way back in 2015. Watch this. So we have a big fireball here. See that? This is a Geminid meteor burning up in the atmosphere. And look at the next frame. What's that? Do you see a line there? That line is smoke or a meteor trail. Watch this. See how it floats away? Look at that. Isn't that neat? So yeah, Geminids will often leave smoke trails. You know, and there's some debate about the word smoke in this context. It's supposed to be trains or trails. I forget which the correct word is, but I just call it smoke because it kind of is smoke. And what's neat is you can see it. You can actually see it floating away in the upper atmosphere. By the way, this is quite a long video. This is like an hour of time. So it's pretty slow, isn't it? Up in the stratosphere. Yeah, isn't that neat? So yeah, the Geminids often produce these smoky meteors. I just shot some more this last week. I didn't bother putting them on this presentation because they weren't that impressive to watch, but in one single session, I got 3 meteors leaving smoke trails like that. Yeah, pretty neat. Hold that thought. I think I may have showed you guys this in one of the videos. Watch this. This is also from the Geminids. This is a wider field, and you guys see there was a meteor there with smoke, and there's another one. See that? So yeah, Geminid meteor shower is a great show. I recommend if you can deal with a cold. So check it out. Yeah. And also if you can deal with the lack of visibility because of clouds and rain and snow and fog. That's the thing. I've seen a lot of fog this year. Yeah. Slow down that thing there. There you go. All right, my friends. This has actually been a kind of a fun show, and we actually did end up under an hour, although the question and answer time has been a bit over that. Let's do one more question, and then I'm going to wrap it up. Let's see. I'm watching the chat. Fascinating. That's not a question. That's a comment. How dare you? Oh, just kidding. So, anybody? This is your last chance to ask a question. Thanks, Troy. You're welcome. Thanks, all of you, by the way, for coming. Let me do my little YouTube live spiel. Just like any content creator now on YouTube Live, I have to say the whole like and subscribe if you liked your experience and want to subscribe to more like it. It would help out our agency, Washington State Parks, as well. We'd like to see more visitation on our YouTube Live channel. I very much personally like this platform. It's technically very impressive. The quality of the video is excellent. The extremely low latency is fantastic. The fact that I can have actual interaction with the chat, I don't know of any other platform that can actually provide that because the latency is just so low. So yeah, we would like to do more on YouTube Live and more on this particular series. And so yeah, like and subscribe if you wish. All right, how can I get a copy if what you are playing? So the good news is the videos are not deleted. Once the live event ends, you can watch it whenever you want. It stays in our playlist, Goldendale Observations, on the YouTube Live channel. And that's one of the other things I like about YouTube Live is how quickly these videos are available to watch for the latecomers or people that just found out about it after the show already ended. Yeah. If you're asking how you could save the videos, I'm not going to give you instructions on that because it involves piracy, but there are software programs that allow you to save, to download YouTube videos, and maybe you could find one of those with a little Googling, perhaps. You didn't hear that from me. So yeah, very useful for educational stuff like this if you want to save it to show your students, for example. And it's not illegal if you have permission and if it's not copyright. Not everything on YouTube is copyright. Anyway, and by the way, I've actually, as a teacher, used material that was public domain that I got off YouTube. So there is public domain material on YouTube. All right, what is the presentation next week? So we'll be talking about something very timely, the solstice, and because it will be the solstice, and which is timely. It corresponds with a famous holiday that many of you will be observing. So yeah, we'll talk about what that means. Yeah. All right, so with that, I hope you guys have enjoyed yourselves. I hope we, again, learned a few things. Keep your curious minds curious by asking questions and then paying attention to the answers and incorporating those answers into the matrix that is your life. You will learn much in this modern age of wonders if you ask questions, because we are literally surrounded by information. It's almost an overload of information, isn't it? So, with that, I hope you guys get to see the Great Conjunction. Even if it's not on the day in question, maybe a day before, after, a week before, it doesn't matter. Trust me, it looks cool either way. I've already seen it many times. It looks beautiful. I love watching. And I'm going to wish you all a good night.